Hello everyone and welcome to Circular Motion Lesson 3. Now just a quick note, if you haven't already watched Electric Fields Lesson 1, please go away and watch that lesson first, because some of the theory that we've used in that lesson we're going to be bringing over to this lesson here. If you haven't watched Electric Fields 1, then later on in the lesson you're going to struggle to understand exactly what we're doing. So for today's lesson then, we're going to be looking and studying centripetal force and the mathematical application of centripetal force in a little bit more detail. Firstly though, just to recap the equations from last lesson, centripetal acceleration and centripetal force, we remember, both act towards the centre of any circle that a body is moving in. For centripetal acceleration, we've got the equation A is equal to V squared over R, and that was equal to omega squared R as well. For centripetal force, we just applied Newton's second law, or at least the basic version of Newton's second law, F equals ma, and we had the equation centripetal force is m V squared over R, or we can take that as m omega squared R. And those are the equations that we looked at last lesson. Moving on to today's lesson then, the first thing that we need to understand about centripetal force is, as a force itself, it doesn't actually exist. We cannot turn around like we can say with friction or any other of the physical forces. We can't turn around with centripetal force and say that it is a physical force and it's the only force that's acting. Centripetal force is really just a mathematical construct to enable us to understand the motion of any object that's moving in a circle. We must always have some kind of physical force. Whether that be friction or gravity or electrostatic attraction or something like that, there has always got to be some kind of physical force. Now, if that physical force is acting as a centripetal force, in other words, it is acting to keep an object moving in a circle, then we can take the equation for that physical force and we can equate it to centripetal force in order to understand more about the motion of that object. So in order to explore that idea further, we're just going to have a look at 4 different situations, and we're going to think about exactly which force, which physical force is acting in order to keep the objects moving in a circle. Now firstly, we can look at planetary motion. With our planets, we know that we have the force of gravity acting towards the sun. That force of gravity is always acting in towards the centre in order to keep our planets moving in their orbits. Now we're not going to look too much at gravitational force today. That will come much later in the course when we do gravity as a separate topic. Next, if we take the most simple atom that we can think of, the hydrogen atom, we know that we have a proton in the centre and an electron orbiting around the outside. Once again, the electron is orbiting, so there must be a physical force acting. Once again, we know that that physical force acting must be towards the centre of the circle. Now that we've watched Electric Fields 1, we do have a physical equation for that force, and that equation comes from Coulomb's law, which is F is equal to Q1 Q2 over 4 pi epsilon naught r squared. There is our physical equation. Because we know that that force is acting to keep the electron in a circle around the proton, we can equate that to our circular motion forces to our centripetal force equations, and we can understand more about that electron and its motion. We'll come back to that idea a little bit later on. Next one then, we can have a look at a hammer thrower, hammer of course being an Olympic sport. The ball on the end of the hammer is obviously very heavy, and the whole idea is that the athlete will spin it around as quick as they can, release it at a certain point in order to project that hammer as far as possible. Now once he's let it go, it will look at projectile motion, and that's obviously a conversation that we could have had back in year one. But while the athlete is spinning the hammer round, there is a tension acting back down the chain and even through the arms of the athlete themselves in order to keep that ball moving in a circle. And the final example we're going to look at is cars going round a roundabout. Here there is a frictional force acting in towards the centre of the roundabout. Now that friction force will come between the tyres and the road itself. Either way, there has to be that frictional force, once again, acting in towards the centre of the circle to keep those cars going around the roundabout. So now that we've had a look at a few different examples of exactly how centripetal force acts, or how we have to have a physical force acting as a centripetal force, let's come back to the hydrogen atom and let's have a look at this in a little bit more detail. As we said then, we know that we have to have a force acting from the electron towards the proton in order to keep that electron orbiting in the atom itself. We know from electric fields 1 that that force, or at least the equation from that force, is Q1 Q2 over 4 pi epsilon naught r squared. That of course from electric fields 1 is Coulomb's law. Now we saw in electric fields 1 that Coulomb's law will apply whenever we have two charges. We could have two static charges. Coulomb's law as a force will still act in between those two charges. In our example though, this force is acting in order to keep the electron orbiting around the proton. It is therefore acting as a centripetal force. Mathematically, therefore, we can take Coulomb's law, this force that we've just written on the screen, and we can equate that to either of our equations for centripetal force. Either mv squared over r or m omega squared r. Let's say for the purposes of this quick example that we want to find out the time period of orbit of that electron. How can we work that out? Looking at centripetal force, we don't immediately see time period, but we remember that omega is equal to 2 pi over t. We can now start to put ourselves an equation together. We start off with Coulomb's law. So we start off again with Q1 Q2 over 4 pi epsilon naught r squared. Because it's acting as a centripetal force, we can therefore equate it to one of our equations for centripetal force, and here, for the purposes of this example, we're going to use m omega squared r. We want t, we want time period, and we know that omega contains time period in there. Omega, of course, being 2 pi over t, we need to remember to square it, so omega squared will be 4 pi squared over t squared. We can now amend our equation to say that Coulomb's law, Q1 Q2 over 4 pi epsilon naught r squared, is equal to m times r times 4 pi squared over t squared. Now at that point, in order to calculate t, we need to make sure that we know everything, we understand everything. A lot of what we see on the screen are constants will be given to you, so the charges will be given to you. 4 and pi and epsilon naught are all constants. M is a constant, 4 and pi squared are constants. If you were asked to work it out, of course, the radius of our hydrogen atom you would be given. At that point, we know everything in that equation, and we can hopefully easily be able to calculate what T is. So let's now put that example and put that idea into practice. And here's a question for you. As usual, you can pause the video, have a go at it yourself, grab a piece of paper and try it out, see what you get for an answer, and when you're ready, come and unpause the video and I'll go through the answer myself. So it says that the radius of a hydrogen atom is 53 picometers. Calculate the speed of the electron as it orbits the nucleus. Pause the video now and have a go yourself. So hopefully you've done that by now, and let's now look at the answer to this question. Just like we've just seen then, we need to take our physical equation and equate it to our centripetal force equation. We know from our last example that the equation that we're looking for from the physical force is Q1 Q2 over 4 pi epsilon naught r squared. Now, because we're looking for the speed of the electron as opposed to the time period or anything else like that, the best equation to take from the centripetal force point of view is going to be mv squared over r. So I'm going to equate Coulomb's law to that. F is equal to mv squared over r. Now, before we go on, some of you at this point might be quite tempted to start plugging numbers into the equation. One of the key skills that we need to understand at year 13, at year 2 physics, is that sometimes we've got to take an algebraic method first. I immediately look at the screen and notice that we've got r on the bottom of our equation on each side. Therefore, this r on the bottom of centripetal force equation will cancel with one of the r's here in Coulomb's law. I'm also going to take this mass, and if we divide both sides by mass, it will get it onto the bottom of the equation. Our equation therefore becomes v squared is equal to Q1 Q2 over 4 pi epsilon naught r multiplied by mass, where the mass here will be the mass of the electron. We can now plug some numbers in. Remember, the charges of our electron and proton are both 1.6 times 10 to the minus 19. So we square it and we divide it by 4 pi multiplied by 8.85 times 10 to the minus 12, that's epsilon naught, multiplied by our radius. Well, the question tells us that's 53 picometers, so 53 times 10 to the minus 12 meters. And we also need to multiply by the mass of the electron, 9.11 times 10 to the minus 31 kilograms. Once we plug all that into the calculator, and obviously don't forget that we need to square root our answer because we were calculating v squared, we get our final answer for speed, once we've rounded it, to be 2.18 times 10 to the 6 meters per second. That, of course, is a perfectly reasonable answer. That's obviously just under 1% of the speed of light, so 10 to the 6 meters per second as an order of magnitude hopefully makes perfect sense. So that's it for this lesson. Hopefully you've got something out of it. Let's just summarise it anyway. Remember then, whenever we have an object moving in a circle, there always has to be some kind of physical force acting to keep it in a circle. Whether that be friction, gravity, tension, whatever it's going to be, there is always that physical force. What you need to do is understand that we can take the equation for the physical force and we can equate it to the equation for centripetal force. And once we've made that distinction and once we've equated those two things, we can do the maths, we can do the algebra, put the numbers in order to understand something more about the motion of that object that's moving in a circle. Now that is the end of the lesson. There is an extension question in a separate video if any of you want it. If you don't want to have a look at the extension question, that's fine. But I suggest for any of you who are aiming for maybe an A or an A star in your A level, that you at least have a look at the extension question and have a go at it yourself.